On a clear night, far from city lights, if you lie on your back and stare upward long enough, your brain does something strange. It starts to feel the distance, not understand it, not calculate it, feel it, in the same primitive, wordless way that you feel the depth of a cliff edge when you stand too close to it. A physical unease, a vertigo that has nothing to do with your inner ear, and everything to do with the sudden, visceral recognition that the points of light scattered across that darkness are not close, that they are not merely far away in the ordinary sense, the way a distant mountain is far away, or a ship disappearing over the horizon, that they occupy a category of distance that your nervous system was never equipped to process. Your brain evolved on a savanna. It was built over hundreds of millions of years of selection pressure to navigate distances measured in meters and kilometers. To judge the speed of a running animal, the gap between two branches, the distance to the next water source. It was not built for light years. It was not built for the kind of distance where even moving at the fastest speed that physics permits. The speed of light, 300,000 kilometers per second, fast enough to circle the Earth 7 times in a single second. The journey to the nearest star still takes over 4 years. 4 years. At the speed of light. And a light, of course, is not a speed that human beings have ever achieved. Not even remotely. The fastest spacecraft ever launched by humanity, the Parker Solar Probe, which at its closest approach to the Sun reaches speeds that make it the fastest human-made object in history, travels at a maximum velocity of approximately 690,000 kilometers per hour. Impressive beyond almost any comparison in human experience. The speed of light is 1.08 billion kilometers per hour. The Parker Solar Probe is traveling at roughly 0.064% of the speed of light. At that speed, the journey to the nearest star, Proxima Centauri, 4.24 light-years away, the closest stellar neighbor our Sun has, would take approximately 6,300 years. 6,300 years. The oldest known writing system on Earth is approximately 5,000 years old. The pyramids of Giza were built roughly 4,500 years ago. 6,300 years ago, human civilization as we would recognize it, cities, agriculture, written language, organized states, did not yet exist in most of the world. And that is the journey to the nearest star, the closest one. Of the estimated 200 to 400 billion stars in the Milky Way galaxy alone, Proxima Centauri is our immediate neighbor, practically next door in galactic terms. And reaching it at the fastest speed any human-made object has ever achieved would take longer than recorded human history. This is the problem. Not a problem in the engineering sense. Not a challenge to be solved with sufficient investment and clever design, though the engineering dimensions of it are real and we will examine them carefully. The problem is deeper than engineering. It is a problem in physics, in biology, in the fundamental relationship between the kind of creature we are and the kind of universe we inhabit. The universe is, to a degree that is almost impossible to fully absorb, enormous. And we are, to a degree that is equally difficult to absorb, slow. And everything about what we are, our bodies, our lifespans, our social structures, our psychology, our dependence on Earth's specific gravity and radiation environment and atmospheric chemistry, was built for a planet. For one particular, Small, warm, wet, magnetically shielded rock orbiting one particular, medium-sized, middle-aged star in the outer arm of one particular galaxy. We were not built for the space between stars, and the space between stars may not care about that at all. This video is about the full depth of that problem, not the surface level version, not just space is really big and we're really slow, though those things are true, and we will quantify them precisely. The full version. The version that takes seriously every dimension of why interstellar travel, even to the nearest star, represents not just a technological challenge, but a confrontation with the most fundamental constraints of the physical and biological universe. And because this story deserves to be told honestly, the version that also looks hard at what, if anything, might make it possible anyway. Let us start with the distance. Really start with it. Chapter 1. The distance, properly understood. There is a number that is used so casually in popular science that its meaning has been almost entirely hollowed out by repetition. That number is 4.24 light-years. It is the distance to Proxima Centauri, the closest star to our Sun. It is the number that anchors virtually every serious discussion of interstellar travel, because if we cannot reach this star, the nearest one, in the most favorable possible case, then the broader project of human expansion into the galaxy does not exist. 4.24 light-years. The distance that light travels in 4 years, 2 months, and roughly 12 days. The problem with this number, stated in those units, is that it is still abstract. Light years are not a unit that connects to anything in ordinary human experience. They are a unit defined by physics, by the speed of a massless particle in a vacuum. And so they carry the disembodied quality of physics. They tell you the size of the thing without making the size of the thing real. So let us make it real. 1 light year is approximately 9.46 trillion kilometers. Trillion with a T. That is 9,460,000,000,000 kilometers. If you drove a car at highway speed, continuously, without stopping, the journey of 1 light year would take approximately 10.7 million years. Not 10.7 years. Not 10.7 thousand years. 10.7 million years, roughly twice the amount of time that has elapsed since our ancestors diverged from the lineage that became chimpanzees. Multiply that by 4.24, and you have the distance to Proxima Centauri in driving terms. Approximately 45 million years of continuous highway driving. The Earth is 4.5 billion years old. The distance to our nearest stellar neighbor, translated into driving time at highway speed, is equivalent to roughly 1% of the entire age of our planet. If that still does not make the scale real, and I suspect it does not, because our intuition for geological time is not much better than our intuition for light years, try it this way. Reduce the entire solar system to a scale model. Put the sun as a basketball in the middle of a football field. On that scale, the Earth is a peppercorn about 26 meters from the basketball. Pluto, the outer edge of what most people think of as our solar system, is a poppy seed about 1 kilometer away from the basketball. The edge of the Oort cloud, the outermost region of material still gravitationally bound to our sun, is roughly 20 kilometers away from the basketball. And on that same scale, the scale on which the sun is a basketball and the entire solar system fits within 20 kilometers, Proxima Centauri is approximately 7,000 kilometers away from the basketball. 7,000 kilometers. In a scale model where the sun is a basketball, the nearest star is on the other side of the planet. The gulf between stars is not merely large. It is of a qualitatively different order of magnitude than anything within a solar system. It is the kind of distance that makes the outer planets of our own system, which we once considered unreachably remote, seem like suburbs. And here is what makes this even more difficult. Proxima Centauri is the best case, the nearest star, the one we would target first if we were launching an interstellar mission. The other stars of the galaxy, the ones that, in our increasingly detailed astronomical surveys, are turning up potentially habitable worlds with increasing frequency, are distributed at distances of tens, hundreds, thousands, and in some cases tens of thousands of light years from Earth. The Milky Way galaxy is approximately 100,000 light years in diameter. If we could somehow travel to Proxima Centauri in what we would consider a reasonable human time frame, let us say 50 years, roughly a lifetime, we would still need 50,000 generations of continuous space travel at that speed to cross the galaxy from one side to the other. 50,000 generations. Homo sapiens as a species has only existed for approximately 300 to 400 generations. This is the scale, and it matters to hold it clearly in mind as we move through everything that follows, because every proposed solution to the problem of interstellar travel, every engine design, every navigation strategy, every life extension scheme, every generation ship concept has to be evaluated against this actual scale. Not the pop science version of it, not the version that feels manageable because we have been told it enough times that the numbers have become familiar. The actual, fully understood, properly digested scale of what we are talking about. We are talking about distances that, at the highest velocities ever achieved in human history, require thousands of years to traverse. And we have not even started talking about the hardest problems yet. Chapter 2: The Tyranny of the Rocket Equation. If the distance to the nearest star is the first wall, the one that makes you understand the scale of the problem, then the rocket equation is the second wall. And in some ways, it is more discouraging than the first, because the first wall is imposed by physics in the sense of the universe being very large. The second wall is imposed by physics in the much more specific sense of mathematics being unforgiving. The rocket equation was derived by Konstantin Tsiolkovsky in 1903, the same year the Wright brothers flew at Kitty Hawk. It is one of the most elegant and most frustrating equations in all of applied physics. What it describes, in essence, is the relationship between how fast a rocket can go, how much fuel it carries, and how efficiently that fuel is burned. And what it tells you, when you push it to the limits required by interstellar travel, is something that engineers who have spent their careers in propulsion call the tyranny. The equation is logarithmic, which means that the relationship between fuel and velocity is not linear. It does not take twice as much fuel to go twice as fast. It takes exponentially more fuel to achieve each incremental increase in velocity as a fraction of the fuel-to-payload ratio becomes more extreme. The faster you want to go, the more fuel you need. The more fuel you carry, the heavier the spacecraft. The heavier the spacecraft, the more fuel you need to accelerate it. The more fuel you need to accelerate it, the more fuel you need to carry that fuel. And on in a feedback loop that becomes explosive at the velocities required for meaningful interstellar travel. Let us put numbers on this. The most efficient rocket propulsion systems currently operational, the best chemical rockets, burning liquid hydrogen and liquid oxygen, have an exhaust velocity of roughly 4.5 kilometers per second. The Saturn V that sent humans to the moon was one of the most powerful rockets ever built. Its mass at launch was approximately 2,800 tons. Its payload delivered to the moon was approximately 45 tons. The Apollo spacecraft. The ratio of total launch mass to delivered payload was roughly 62 to 1. You needed 62 kilograms of rocket, fuel, structure, engines, for every kilogram you delivered to lunar orbit. Now apply the rocket equation to interstellar travel. To reach even a modest fraction of the speed of light, let us say 10%, or 30,000 kilometers per second, using the best chemical propulsion, you would need a fuel-to-payload ratio that is, in practical terms, infinite. There is no amount of fuel that is physically large enough. The rocket required to reach 10% of the speed of light using chemical propulsion would need to be composed almost entirely of fuel, with essentially no room for the spacecraft, the crew, the life support, or anything else. And the fuel itself would need to be accelerated by more fuel, which would need to be accelerated by more fuel until the required initial mass becomes larger than anything that could possibly be assembled or launched from Earth's surface. Chemical propulsion, to be direct about it, does not work for interstellar travel. It is not a matter of scaling up existing technology. It is a fundamental mismatch between the energy density of chemical reactions and the velocities required. What about nuclear propulsion? This is where things get more interesting and where the history of human technological ambition and the constraints of political reality intersect in a way that is both fascinating and melancholy. In the 1950s and 1960s, a group of American physicists working on a classified program called Project Orion developed a propulsion concept that was, by the standards of any realistic assessment, genuinely audacious. The idea was to propel a spacecraft by detonating nuclear bombs behind it, a series of atomic explosions, each one pushing the spacecraft forward via a massive steel pusher plate equipped with enormous shock absorbers. The energy density of nuclear weapons is vastly greater than chemical propulsion. The concept was mathematically coherent. The physicists who worked on it, including Freeman Dyson, one of the most brilliant theoretical physicists of the 20th century, believed it could work. Dyson estimated that an Orion spacecraft could reach Proxima Centauri in approximately 130 years, using the nuclear pulse propulsion concept. The program was canceled in 1963, primarily as a consequence of the Partial Nuclear Test Ban Treaty, which prohibited nuclear detonations in space. And the political and practical obstacles to detonating hundreds or thousands of nuclear weapons in the vicinity of Earth to launch an interstellar mission remain, to put it gently, significant. More recently, serious scientific and engineering attention has focused on two other propulsion concepts that could, in principle, achieve the velocities needed for interstellar travel within human timescales. The first is fusion propulsion, nuclear fusion, the same process that powers the sun. The combination of hydrogen nuclei into helium with the release of enormous amounts of energy has an energy density approximately 4 million times greater than the best chemical propulsion. A fusion rocket burning a deuterium-helium-3 fuel mixture could, in principle, achieve exhaust velocities and mass ratios that would allow a spacecraft to reach a significant fraction of the speed of light. The specific impulse of a fusion drive, the measure of how efficiently it uses its fuel, is orders of magnitude better than any chemical system. The problem is that we do not yet have functioning fusion propulsion. We do not, as of this writing, have functioning fusion power generation of any kind, despite 6 decades of intensive research. The most advanced fusion research programs in the world, the ITOR project in France, the National Ignition Facility in California, the private fusion ventures that have attracted billions in investment in recent years, are making real and accelerating progress. But the gap between achieved sustained fusion ignition in a laboratory setting and built a fusion rocket capable of accelerating a crewed spacecraft to 10% of the speed of light is enormous. It involves not just the fusion physics, but the engineering of systems that could operate at those energy levels for years in deep space, the heat management, the magnetic containment, the fuel processing. It is a frontier of engineering that does not yet exist. The second concept, and the one that has attracted perhaps the most serious scientific attention in recent years, is the light sail, a spacecraft propelled not by any onboard fuel at all, but by the pressure of photons from a powerful directed energy source, typically a large phased array laser aimed at an extremely large, extremely thin reflective sail. The Breakthrough Starshot initiative, announced in 2016 by a consortium that included the late Stephen Hawking, proposed exactly this: a fleet of gram-scale spacecraft attached to meters-wide laser sails, accelerated to approximately 20% of the speed of light by a ground-based laser array with a combined power output in the gigawatt range. At 20% of the speed of light, the journey to Proxima Centauri takes approximately 20 years. The physics works, the mathematics is compelling, and the engineering challenges are, to put it charitably, extraordinary. The laser array required would need to be among the largest and most powerful engineering structures ever built by humanity. A kilometer-scale phased array capable of maintaining coherent beam focus over a distance of tens of millions of kilometers. The sail material must be reflective enough to survive the beam without absorbing enough energy to vaporize, light enough to be accelerated to the required velocities, and structurally coherent enough to maintain its shape during the acceleration phase. The gram-scale spacecraft would need to carry instruments capable of meaningful scientific observation of another star system and a communication system capable of transmitting data across 4.24 light-years. And the gram-scale constraint means there is essentially no room for anything approaching a human crew. Breakthrough Starshot, as proposed, is not a crewed interstellar mission. It is a probe mission, a robotic scouting expedition. The idea is to send instruments, not people, and even the instrumented version faces engineering challenges that have not been fully solved. For crude interstellar travel, the light sail concept, as currently conceived, does not apply. A human being masses approximately 70 kilograms. Life support for years of interstellar transit would mass orders of magnitude more. The sail area required to accelerate a crewed spacecraft at the required power level scales in ways that quickly reach the physically impractical. You are not pushing a gram. You are pushing a city. This is what the tyranny of the rocket equation looks like at interstellar scales. Every approach that works in principle faces engineering challenges that are, with current or near future technology, essentially unsolvable. Every approach that is technically tractable today, chemical propulsion, even nuclear propulsion, falls orders of magnitude short of the velocities needed to make interstellar travel conceivable within human lifetimes. We have not yet touched the biological problems, and the biological problems are, in many ways, more fundamental than the propulsion problems. Chapter 3: The body at the edge of everything. The human body is an extraordinary machine. It is the product of 3.8 billion years of evolutionary refinement. The accumulated biological learning of every organism that ever lived on this planet, distilled through the merciless filter of natural selection into a system of staggering complexity, and, within its design parameters, remarkable reliability. The key phrase there is within its design parameters, because the human body was designed, if we can use that word loosely to describe the outputs of evolutionary pressure, for one very specific environment: Earth's surface. One specific gravity, 9.8 meters per second squared. One specific atmospheric composition, roughly 21% oxygen and 78% nitrogen at one specific pressure. One specific magnetic field strength, which deflects the solar and cosmic radiation that would otherwise bombard the surface. One specific range of temperatures. One specific diurnal cycle of approximately 24 hours, to which our entire circadian biology is tuned. One specific level of background radiation, low enough that our DNA repair mechanisms can handle it without accumulating damage faster than they can correct it. Remove any one of these conditions, and the body begins to fail. Not metaphorically, physiologically, in specific, documented, measurable ways that get worse the longer the exposure continues. We have already discussed, in the context of the Artemis missions, what microgravity does to the human body over months and years. The bone density loss, 1 to 2% per month in weight-bearing bones, a rate comparable to severe osteoporosis. The muscle atrophy that begins within days of weightlessness. The cardiovascular remodeling as the heart loses the load it was built to pump against. The fluid redistribution that pushes fluid toward the head and chest, producing the chronic nasal congestion and the facial puffiness that every long-duration astronaut knows, and the more serious downstream consequence of spaceflight-associated neuroocular syndrome, the chronic intracranial pressure that, over months, reshapes the eyeball and damages the optic nerve. An interstellar spacecraft, unless it incorporates artificial gravity, which requires either constant acceleration or a rotating habitat, both of which have substantial engineering and mass implications, will be a microgravity environment for its entire journey. For a journey of years or decades or centuries, the microgravity effects on the human body are not a management problem. They are a biological death sentence. The countermeasures that are used on the ISS, rigorous daily exercise programs, slow the deterioration but do not halt it. Over timescales of years in true microgravity, without a much more radical biological intervention than anything currently available, the human body will degrade beyond the point of functional recovery. But microgravity is not even the most serious biological threat in interstellar space. That distinction belongs unambiguously to radiation. In the deep space between stars, in the true interstellar medium, beyond even the protective bubble of the heliosphere that our sun creates around our solar system, the galactic cosmic ray environment is relentless and severe. The heliosphere, created by the solar wind, actually provides a degree of shielding against low-energy cosmic rays that we lose entirely once we leave the solar system. Beyond the heliopause, the boundary of our sun's influence, at roughly 120 to 150 astronomical units from the sun, the spacecraft is in the full, unattenuated interstellar radiation environment. Galactic cosmic rays are nuclei of atoms, primarily hydrogen and helium, but also heavier elements up to and including iron, stripped of their electrons and accelerated by supernovae and neutron star collisions to velocities approaching the speed of light. They carry energies that range from millions to billions of electron volts per nucleon, and the heaviest, most energetic ones, the high Z, high energy, HZE particles, are essentially impossible to shield against with any passive shielding material. This is not a matter of building thicker walls. The problem with HZE particles is that they are so energetic that they penetrate even meters of solid material, and their interaction with shielding actually makes the problem worse. When an HZE particle hits a dense shielding material, it does not simply stop. It undergoes nuclear fragmentation, producing a shower of secondary particles, neutrons, gamma rays, lighter nuclei, that can deliver doses higher than the original particle would have, in a wider spatial distribution. This phenomenon, called secondary particle production, means that simply adding more conventional shielding above a certain thickness makes the radiation environment inside the spacecraft worse, not better. The only shielding approaches that do not suffer from this problem involve either hydrogen-rich materials. The light elements are more effective at absorbing cosmic ray energy without producing harmful secondaries, or active magnetic shielding, which deflects the charged cosmic ray particles before they reach the spacecraft by generating an artificial magnetosphere around it. Hydrogen-rich shielding adds mass proportionally. You need a lot of it, and mass is the enemy of propulsion. Active magnetic shielding requires superconducting coils, generating enormous magnetic fields, operating continuously at the cryogenic temperatures required for superconductivity for years or decades in deep space. The engineering of this system does not yet exist at the scale required. The biological consequences of the interstellar radiation environment over a multi-year transit are, on the basis of current knowledge, severe. The cancer risk from total accumulated dose is significant. But as we discussed in the context of Artemis, the more immediately alarming finding from recent research is what the HZE particles do to the central nervous system. The direct neuronal damage from heavy ion radiation, the track of cellular destruction that a single iron nucleus traveling at near light speed leaves through brain tissue, is not primarily a cancer risk. It is a cognitive impairment risk. Degradation of the prefrontal cortex, memory loss, increased anxiety, impaired decision-making. All of this accumulating progressively over the duration of a long interstellar transit in an environment where the radiation dose is higher and less well shielded than anything experienced in low Earth orbit or even on the lunar surface. The astronauts on an interstellar spacecraft would, over the course of their transit, be experiencing ongoing neurological damage, not from a single acute event, but from the continuous cumulative biological cost of living in the interstellar radiation environment for years. And the people whose cognitive function is being degraded are the people responsible for operating the spacecraft, making critical decisions, managing emergencies. The crew whose judgment is most needed is the crew whose judgment is being systematically eroded by the environment they are in. This is not a solvable problem with current biology and current shielding technology. It is a hard limit. And then there is time. Chapter 4, the lifespan problem. Of all the constraints on interstellar travel, the one that is most fundamentally human, most rooted in the specific, irreversible biology of what we are, is the constraint of lifespan. Human beings live in the absence of disease and accident, and with the benefits of modern medicine, approximately 80 to 90 years. Some live longer. Exceptional individuals have reached 120. No verified human being has ever lived to 130. The fastest trajectory to Proxima Centauri, achievable with propulsion concepts that are physically coherent and not wildly beyond current engineering, accounting for realistic mass budgets and power requirements, would take somewhere between 20 and 100 years, depending on which specific concept you're evaluating. The breakthrough star-shot light sail at 20% of the speed of light takes 20 years, but it cannot carry a crew. A fusion drive spacecraft achieving 10% of the speed of light takes roughly 43 years. A more near-term nuclear electric propulsion system achieving something like 5% of the speed of light takes about 85 years. And these are journey times in the reference frame of the distant observer, someone watching from Earth. For the crew on board at the velocities involved, relativistic time dilation becomes meaningful. At 10% of the speed of light, a journey that takes 43 years on Earth clocks takes approximately 42.8 years on the spacecraft. The dilation is only about 0.5%. It is not the magic carpet that science fiction has sometimes presented relativity as providing. To get meaningful time dilation, the kind where decades pass on Earth while only years pass on the spacecraft, you need to travel at velocities above 50 to 90% of the speed of light. And getting to those velocities with a crewed spacecraft, for the reasons we have discussed, is the hardest engineering problem in the history of humanity by several orders of magnitude. So for the propulsion systems that are actually tractable, the ones that do not require building an engineering infrastructure that dwarfs anything our civilization has yet created, the journey to even the nearest star takes the majority of a human lifetime, or more than a lifetime, or much more than a lifetime. What does this mean in practice? It means that the crew of an interstellar spacecraft departing today would, in most scenarios, never arrive. They would age, They would grow old in transit. They would die in deep space decades before the spacecraft reached its destination. If the journey takes 80 years, you launch as an infant and arrive as an old person, assuming the biological effects of decades in deep space have not already ended the mission. If it takes more than 80 years, you launch knowing that you personally will not survive to see the destination. Your children might. Your grandchildren almost certainly will, if the mission is designed to sustain reproduction across generations. But the people who arrive will not be the people who left. This is the generation ship concept, which we will examine in detail. But first, let us sit with the simpler version of the problem. Even for a journey that is just barely within a single human lifespan, the most optimistic, scenarios for fusion or antimatter propulsion, the ones that require technologies substantially beyond current capability. The nature of the mission changes fundamentally from any kind of exploration we have ever conducted. The entire history of human exploration, from the first migrations out of Africa to the voyages of the Age of Discovery to the Apollo missions, has been characterized by a relationship between the explorers and their home, a connection, a tether, psychological and eventually physical. The explorers went and they came back, or they maintained communication, or they established new settlements within reach of the world they came from. The knowledge that home existed, that it was reachable, that news could travel back and forth. This has been the background condition of every human exploratory venture in history. An interstellar mission breaks that tether permanently. At the distance of Proxima Centauri, communications travel at the speed of light, the maximum possible speed. A message sent from the spacecraft to Earth takes 4.24 years to arrive. A reply takes another 4.24 years to return. The round-trip communication delay is 8.48 years. If a medical emergency occurs on the spacecraft, the crew cannot ask Earth for help and receive a response in any medically relevant timeframe. If a technical system fails, the engineering team on Earth cannot diagnose it in real time. If a crew member has a psychological crisis, the psychologist on Earth cannot provide immediate support. The spacecraft and its crew are not isolated the way the ISS is isolated, where a Soyuz return is available and Earth support is in real-time radio contact. They are isolated in a way that no human expedition has ever been, at distances that make the concept of rescue not just difficult, but physically impossible. The psychological dimensions of this isolation are not theoretical. They are the subject of serious research programs. NASA's long duration isolation studies, the Mars 500 confinement simulation, the Antarctic winter overstudies, and what those programs consistently find is that extended isolation in a closed environment without the psychological anchors of meaningful connection to the outside world produces a recognizable syndrome of cognitive and emotional deterioration that builds over months. Anxiety, depression, cognitive rigidity, interpersonal conflict. The kind of slow, grinding psychological erosion that comes from being confined in a small space with the same small group of people, with no variation in environment, no novelty of landscape or social contact, no connection to the rhythms of the world outside. On an interstellar spacecraft, this would be the condition not for months, but for years, or decades, or generations. The monotony, the confinement, the psychological weight of the void outside the windows. These are not small problems to be addressed in a paragraph. They are potentially mission-ending challenges that touch on the most fundamental aspects of human psychology and human need. And then you arrive. If you arrive, if the spacecraft has maintained its integrity for decades in deep space, if the crew has survived the radiation, maintained their health in microgravity, maintained their psychological cohesion through decades of isolation, if the propulsion system has performed as designed for the entire journey, if nothing that could not be repaired with onboard resources has broken beyond the point of repair, you arrive at a star system about which you know only what robotic probes and telescopes have told you. You arrive with no knowledge of whether the conditions are actually habitable, with no rescue available if they are not, with no way to return to Earth on any human timescale. The closest thing to a realistic interstellar arrival scenario, and this is where the conversation shades from the merely difficult to the deeply unsettling, is a one-way trip. Not because the return is physically impossible, but because the energy and time requirements of a return journey, compounded on top of the already immense requirements of the outward journey, make it essentially equivalent to a second, independent interstellar mission. You go, you do not come back. That is the honest version of what interstellar travel to Proxima Centauri looks like for a human being, under the most optimistic propulsion scenarios and the current state of life extension biology. Chapter 5: The Generation Ship, humanity's most ambitious idea. If no single human lifetime can span the distance to the stars, perhaps many lifetimes can. This is the generation ship concept, and it is one of the oldest ideas in speculative thinking about interstellar travel, dating back at least to the 1920s and appearing in serious scientific literature from the 1950s onward. The basic premise is straightforward. Build a spacecraft large enough to sustain a complete, self-sufficient human community, a population of hundreds or thousands of people, with the biological diversity, the food production, the social structures, the knowledge base, and the reproductive capacity to persist across many generations, and launch it toward a distant star. The original crew grows old and dies aboard the ship. Their children are born aboard the ship. Their children's children are born aboard the ship. Dozens of generations later, the descendants of the original crew arrive at the destination, having spent their entire lives in transit. It is, in its ambition and its melancholy, one of the most extraordinary ideas the human species has ever conceived. And when you examine it with the full rigor of physics, biology, psychology, sociology, and systems engineering, when you stop treating it as a science fiction premise and start treating it as an engineering proposal, it becomes one of the most complex and challenging ideas the human species has ever tried to make operational. The first problem is scale. A generation ship must be self-sufficient in a way that no human habitat in the history of our species has ever had to be. Every modern human community, every city, every town, every remote research station, is embedded in a web of supply chains, external knowledge resources, and trade relationships that it depends on for its function. The Antarctic research stations, the most isolated permanent human habitats on Earth, receive regular supply flights and maintain continuous communication with the outside world. The ISS is resupplied and crewed on a schedule of months. A generation ship has no supply chain. It has no resupply. Everything the crew will need for the entire journey, which may be a century or more, must either be carried aboard at launch or produced from resources available on the spacecraft. Food must be grown continuously in agricultural systems that have never failed for more than a day without causing a crisis for a century. Water must be recycled with efficiencies approaching 100% indefinitely. Atmosphere must be maintained. Structural systems must be repaired. Medical care must be provided across the full spectrum of human disease and injury without access to the full infrastructure of a hospital. Technology must be maintained and eventually replaced in an environment where spare parts cannot be ordered, and manufacturing depends entirely on the capabilities built into the ship. The engineering required to build a closed ecological life support system, what NASA calls a bioregenerative life support system, that can operate at the required efficiency and reliability for a century or more in deep space, is beyond anything currently demonstrated. The best closed-loop life support systems we have built on the ISS, in the Biosphere 2 experiment, in various NASA research programs, have all required external intervention, resupply, or correction at some point. The Biosphere 2 project, an attempt to create a fully enclosed biosphere in the Arizona desert in the 1990s, experienced oxygen depletion, species die-offs, and agricultural failures that forced external intervention within months of its planned multi-year operation. 100 years with no external intervention. That is the requirement. And it is a requirement that we have not demonstrated at any scale. The second problem is population genetics. This one is less intuitive but equally serious. A viable founding population for a multi-generational voyage requires sufficient genetic diversity to prevent the accumulation of harmful genetic variations through inbreeding and genetic drift. The statistical process by which rare alleles become more or less common purely by chance as small populations reproduce. The loss of genetic diversity in a small, closed population is not a matter of degree. Over enough generations, it inevitably produces the genetic equivalent of an island. Population after a bottleneck. Reduced diversity, increased expression of recessive deleterious traits, reduced adaptive capacity to disease, and environmental change. Population geneticists who have studied the generation ship problem specifically have produced widely varying estimates for the minimum viable founding population, depending on the assumptions made about reproductive patterns, selection effects, and the duration of the voyage. The most commonly cited minimum, the number often appearing in serious scientific papers on the subject, is around 150 to 180 individuals, based on models of the genetic diversity maintained across a voyage of roughly 200 years. More conservative analyses, accounting for the full range of random genetic drift effects over longer timescales and the possibility of significant disease events, suggest populations of 500, 1,000, or even several thousand are required to maintain the genetic health of the population across 10 or more generations. For a 10-generation voyage with a founding population of 500 people, and remember, this is a conservative estimate for maintaining genetic health, not a luxurious margin, the spacecraft must support 500 people, their food production, their life support, their medical care, and their social and psychological needs for the duration. The mass requirements for this, the food production systems, the water recycling, the atmospheric management, the habitat volume required for 500 people to maintain psychological health over a century, are enormous. And mass, as we have discussed, is the fundamental enemy of propulsion. The third problem is social and institutional stability, and this one is, in its own way, the strangest. How do you motivate the middle generations? The founding generation, the people who chose to get on the ship, have a relationship to the mission that is direct and personal. They made the decision. They have the connection to Earth that they are leaving behind, and the vision of the destination that they are seeking. Their psychological investment in the mission is their own. The arriving generation, the descendants who actually reach the destination, have a relationship to the mission that is also comprehensible. They will be the ones who step out into a new star system. They will be the ones who fulfill the purpose of the voyage. But the middle generations, the people who are born in deep space, live their entire lives in deep space, and die in deep space, having never seen Earth and having no possibility of seeing the destination, have a relationship to the mission that is philosophically extraordinary and psychologically unprecedented. They did not choose to be born on a spacecraft. They cannot choose to leave. Their entire lives are defined by a goal set by people who lived before them and to be achieved by people who will live after them. They are, in a very literal sense, instruments of a multi-generational project whose beneficiaries are not themselves. The question of whether such a society is ethically defensible, whether the founding generation has the right to commit their descendants to this mission without their consent, is one that philosophers and ethicists have wrestled with seriously. The conclusion is not obvious. Children do not consent to many things that shape their lives. The country they are born into, the religion they are raised in, the economic conditions of their families. But there is a difference between being born into conditions you did not choose and being born into conditions that you cannot escape and that define your entire existence and that were chosen specifically to produce your sacrifice for a goal that others will benefit from. The generation ship, examined honestly, is not just an engineering challenge. It is a philosophical challenge. It asks what we owe to the people we create and whether we can create people specifically to serve as the living mechanism of a mission they cannot exit. These are not questions with easy answers. And they are not purely hypothetical, because the generation ship, if it is ever built, will be populated by real human beings with real psychological needs, real social dynamics, real conflicts, and ambitions and desires. The ship's society will not remain static across generations. It will change. It will develop its own culture, its own institutions, its own understanding of history and mission. It may, after enough generations, begin to drift from the values and goals of its founders. It may, in the worst case, forget where it is going and why. The speculative literature on generation ships, the serious scientific literature, not just the science fiction, includes analyses of the conditions under which mission integrity might be maintained across multiple generations. The conclusions are sobering. The longer the voyage, the greater the social drift. The larger the founding population, the more diverse the social dynamics and the harder to maintain consensus. The more isolated the community, the more intense the interpersonal conflicts that build over generations in enclosed spaces. A generation ship is not a spacecraft. It is a civilization, a small, sealed, isolated, resource-constrained civilization hurtling through the void at a fraction of the speed of light, and building a civilization that remains stable and purposeful across 10 or 20 or 50 generations, without any possibility of outside intervention or resupply or cultural exchange, is not an engineering problem. It is the hardest social problem in human history. There is a thought experiment that captures the full weight of this challenge in a way that abstract analysis sometimes cannot. Imagine you are among the founding generation of the generation ship. You are, let us say, 30 years old when the ship launches. You chose this. You accepted the terms. You understood as fully as anyone can understand something so abstract that you were signing up to live your entire remaining life aboard the spacecraft and to die in deep space without ever seeing your destination. You have children. Your children grow up knowing nothing but the ship. Their world, their entire world, the only world that exists for them, is the interior of a spacecraft. The same corridors, the same faces, the same agricultural bays and maintenance tunnels and recreation areas, day after day, year after year. They cannot go outside. There is no outside, not in any meaningful human sense. There is only the void on the other side of a few centimeters of structural hull, which they know about in the abstract, but have never experienced in any way that their nervous system can process. These children did not choose any of this. They were born into it, and they are being raised to maintain the ship's systems, to continue the voyage their parents started, to pass the mission along to their own children someday. They are being raised, in other words, to be the instruments of a project whose purpose they had no part in choosing and whose benefits they will not live to see. What obligations does the founding generation owe these children? What moral architecture can support the claim that creating a person into permanent involuntary confinement, however purpose-filled, however community-rich, however meaningful the collective mission, is an ethically defensible act? These are not rhetorical questions designed to stop the conversation. They are genuine philosophical problems that any serious proposal for interstellar colonization via generation ship must confront. And the fact that they have not been widely confronted in the popular conversation about interstellar travel is itself revealing, a sign that the popular conversation has been conducted more in the register of adventure than in the register of ethics. The generation ship is humanity's most ambitious idea. It may also be humanity's most morally complex one. Chapter 6: The Physics of Going Faster. At some point in every serious conversation about interstellar travel, someone invokes warp drive, usually as a joke, sometimes as a genuine question. Occasionally, and this is the more interesting case, as a provocation that turns out to be worth taking seriously. Not because warp drive, as depicted in science fiction, is real or achievable, but because the underlying physics it is gesturing at is real, genuinely, rigorously, mathematically real. And understanding what that physics actually says, not the television version, but the equations themselves, is essential to understanding both the outer limits of what might be possible and the vast distance between those limits and anything we can currently do. The relevant physics is the Alcubierre drive, proposed in 1994 by Mexican theoretical physicist Miguel Alcubierre in a paper published in the journal Classical and Quantum Gravity. Alcubierre's idea was elegant in the way that ideas which are technically consistent with the laws of physics but physically preposterous tend to be elegant. He showed, using the mathematics of general relativity, that it is theoretically possible to construct a geometry of spacetime in which a region of flat spacetime, a bubble, is embedded within a distortion field, spacetime compressed in front of the bubble and expanded behind it. Within the bubble, the spacecraft sits at rest. The bubble itself moves through space. And because it is spacetime that is moving rather than the spacecraft within spacetime, the effective velocity of travel is not constrained by the universal speed limit that applies to objects moving through space. The craft is not moving through space at faster than light speed. The space itself is moving. The craft is along for the ride. It is, as I said, mathematically consistent with general relativity. Einstein's equations do not, in principle, forbid this geometry. And, in the 1990s and early 2000s, a small but serious community of theoretical physicists explored the Alcubierre metric with genuine interest, probing its properties and its implications. What they found was a list of problems that begins with requires exotic matter and gets worse from there. Exotic matter is not a science fiction term. It is a specific concept in theoretical physics referring to matter with negative energy density. Matter that, unlike all known matter in the universe, would have a gravitational effect opposite to normal matter. It would repel rather than attract. It would have negative mass. No confirmed example of exotic matter has ever been observed in nature. The closest analog we have, the Casimir effect, in which quantum vacuum fluctuations between closely spaced metal plates produce a measurable attractive force that can be interpreted in terms of negative energy density, operates at scales of nanometers and produces amounts of negative energy density so minuscule that applying it to an Alcubierre bubble is not an engineering challenge. It is a joke. The amount of exotic matter required to maintain an Alcubierre bubble capable of carrying a spacecraft the size of a car to Proxima Centauri has been estimated in various analyses as equivalent to the mass energy of Jupiter, the largest planet in our solar system. In exotic matter. Negative mass exotic matter. That does not exist. But even if we set aside the exotic matter requirement and ask what other problems the Alcubierre drive faces, the list remains extensive. Harold White at NASA's Johnson Space Center spent several years in the early 2000s exploring whether modifications to the original Alcubierre geometry could reduce the exotic matter requirement to more tractable levels, and his work was widely reported in science media with considerable excitement. The honest assessment of where that work landed is that while White's modifications do reduce the theoretical exotic matter requirement, they reduce it from the mass energy of Jupiter to still an amount of exotic matter that does not exist and has never been observed in nature. The reduction is mathematically interesting. It does not solve the fundamental problem. There are other faster-than-light concepts in the theoretical literature. Traversable wormholes, solutions to Einstein's field equations that connect two distant points in space-time through a shortcut, have been studied seriously since the late 1980s, partly because they appear to circumvent the exotic matter problem in a somewhat different way. The mathematics of wormhole stability, however, leads to the same place as the Alcubierre drive. You need exotic matter to hold the throat of the wormhole open, and exotic matter of the required type and quantity does not exist in any form accessible to current or foreseeable human technology. The deeper point here, the one that the physics is insisting on even when the mathematics is still internally consistent, is that general relativity does not merely permit space-time geometries that enable faster-than-light travel. It permits them the same way that a zoning code might technically permit the construction of a building with no structural support. Nothing in the code explicitly forbids it, but the physics of the real world does. The real world enforces its own constraints in ways that the equations do not always make immediately visible. So faster-than-light travel is not available. The speed of light is not a limit that exists because we have not been clever enough or rich enough to circumvent it. It is a limit that exists because of the structure of space-time itself, a structure that, as best we can determine, does not contain the kind of exotic matter needed to warp it in ways that would change that limit, and probably never will. What about going nearly as fast as light? Not faster, but close? 50%? 80%? 90%? This is where the AI, physics of special relativity, becomes genuinely interesting, because at those velocities, the time dilation effects that were negligible at 5 or 10% of the speed of light become substantial. At 90% of the speed of light, the time dilation factor, the ratio between time as experienced by the moving crew versus time as measured by a stationary observer, is approximately 2.3. A journey that takes 4.7 years in Earth time would be experienced by the crew as roughly 2 years. At 99% of the speed of light, the dilation factor is approximately 7. At 99.9%, it is approximately 22. In principle, if you could accelerate a spacecraft to within a fraction of a percent of the speed of light, a human crew could cross the distance to Proxima Centauri in what would feel to them like months. The crew ages months. The universe ages years. They arrive biologically young. If you could somehow push to 99.9999% of the speed of light, you could cross much of the galaxy in a human lifetime. The physics of special relativity genuinely permits this. The biology survives the time dilation. There is no fundamental theorem of physics that forbids a human being from being accelerated to 99.9% of the speed of light and experiencing the resulting time dilation. The problem is the energy. To accelerate a spacecraft with a mass of 1 kilogram, not a crew, not life support, not food, just a single kilogram of mass, to 99% of the speed of light requires kinetic energy, equivalent to approximately 6.3 times 10 to the 17th joules. 630 trillion joules. The total global energy consumption of human civilization for an entire year is approximately 5 times 10 to the 20th joules. Accelerating 1 kilogram to 99% of the speed of light would require roughly 1,000th of the entire annual energy budget of human civilization on Earth. Now scale that up to a crewed spacecraft. A minimal crewed spacecraft. 4 people, life, support for years, propulsion, structure, masses at absolute minimum tens of thousands of kilograms. Realistically, hundreds of thousands. The energy required to accelerate such a spacecraft to a meaningful fraction of the speed of light exceeds the total energy output of the Sun over human timescales, in ways that make the numbers effectively meaningless as engineering specifications. There's one propulsion concept that sits at the intersection of physical possibility and extreme engineering ambition, and that is genuinely worth discussing in detail rather than dismissing. That concept is antimatter propulsion. Antimatter is real. It is produced in particle accelerators and in natural processes. It is the mirror image of ordinary matter. An antiproton has the same mass as a proton, but the opposite charge. When matter and antimatter meet, they annihilate completely, converting their combined mass entirely into energy with 100% efficiency. No other reaction known to physics, not fission, not fusion, not any chemical process, approaches this energy density. A kilogram of antimatter annihilating with a kilogram of ordinary matter releases energy equivalent to the Tsar Bomba, the most powerful nuclear weapon ever detonated approximately 90 times over. The energy density of matter-antimatter annihilation is staggering enough that, if a spacecraft could be designed to use it as propulsion, the fuel mass requirements would be dramatically more tractable than any other concept. A modest antimatter rocket, one carrying enough antimatter to annihilate with a comparable mass of hydrogen fuel, could, in principle, achieve velocities of 50 to 80% of the speed of light with a fuel-to-payload ratio that is at least theoretically achievable. The problem with antimatter propulsion is not the physics. The physics works. The problem is production. Producing antimatter requires particle accelerators. The production rate of antiprotons at CERN, the most productive source of antimatter in the world, using the most powerful particle accelerators humanity has ever built, is approximately 10 nanograms per year, 10 billionths of a gram per year, with the largest scientific instrument complex on Earth running continuously. A minimal interstellar mission using antimatter propulsion would require kilograms or tens of kilograms of antimatter. At CERN's production rate, accumulating the antimatter for a single interstellar mission would require approximately 100 billion years of continuous operation of the world's largest particle accelerators. The age of the universe is 13.8 billion years. We would need to run CERN for roughly 7 times the current age of the universe to produce enough antimatter to fuel one interstellar mission. This is not a problem of investment or political will. It is a problem of physical scale. The energy required to produce the antimatter is far greater than the energy the antimatter would deliver as propulsion, making the entire exercise thermodynamically counterproductive unless you have access to an energy source of extraordinary scale. A Kardashev. Type 2 civilization, one that harvests the entire energy output of its star, could potentially produce antimatter fast enough for interstellar missions. We are currently a fraction of a Kardashev Type 1 civilization, one that has not yet fully harnessed even its own planet's energy resources. The physics of going faster, when you push it to its honest conclusions, keeps returning to the same fundamental message. The speeds required for human interstellar travel within human lifetimes are achievable in principle. The universe does not forbid them, but the energy required to achieve them is so far beyond current and foreseeable human capability that the distinction between physically possible in principle and practically impossible collapses into something that functions as a hard limit for any realistic planning. Horizon. We are not slow because we have not tried hard enough. We are slow because the energy requirements of going fast are written into the laws of physics in ways that cannot be engineered around. Chapter 7. Suspended animation and the biological escape. If the problem of interstellar travel is partly a biological one, the human body ages, deteriorates, and dies on timescales far shorter than most interstellar journeys, then perhaps the solution is not to change the journey, but to change the biology during the journey. This is the suspended animation concept, and unlike faster-than-light travel, it does not require exotic physics. It requires biology. Specifically, it requires the ability to reduce the metabolic rate of a human being to a level at which the normal processes of aging, radiation damage accumulation, and physiological deterioration are either slowed dramatically or halted entirely, and to do so reversibly, to bring the person back to full biological function at the end of the journey. The concept is not purely speculative. Nature has provided multiple existence proofs of metabolic suspension in biological systems. Tardigrades, microscopic animals informally known as water bears, can enter a state called cryptobiosis in which their metabolism essentially stops entirely. They can survive extreme desiccation, extreme cold, extreme radiation, and even the vacuum of space in this state, and then be revived when conditions improve. Wood frogs in North America can survive being almost entirely frozen in winter, with ice crystals forming in their tissues, and their heart and brain activity ceasing, and thaw in spring with full biological function restored. Various bacteria and plant seeds can remain in states of extreme metabolic suppression for decades or centuries, and then be revived. What these organisms demonstrate is that biological systems can, in principle, be suspended and revived. The question for human interstellar travel is whether a similar state can be achieved in an organism as complex as a human being, for durations of years to decades, and reversibly. The gap between a tardigrade entering cryptobiosis and a human being entering medically induced hibernation is, unfortunately, vast. The most relevant medical analog to what interstellar hibernation would require is therapeutic hypothermia, the clinical practice of deliberately reducing a patient's body temperature to slow metabolism and reduce oxygen demand during cardiac surgery or severe traumatic brain injury. Therapeutic hypothermia is real. It is practiced in hospitals, and it demonstrably extends the window during which the brain can survive oxygen deprivation. Patients have been cooled to temperatures as low as 18 degrees Celsius during complex cardiac procedures, and then rewarmed with their neurological function intact. The limitation is duration. Therapeutic hypothermia in clinical practice is maintained for hours, or in some exceptional research contexts, days. The metabolic suppression achieved reduces metabolism to roughly 50 to 70% of baseline at moderate hypothermia. It does not halt aging, It does not halt radiation damage accumulation. It does not halt the subtle, ongoing processes of cellular deterioration that constitute biological aging. It buys time, not suspension. There is a company, SpaceWorks, a NASA contractor, that has been working on a technology it calls torpor-inducing transfer habitat, specifically aimed at enabling long-duration human spaceflight by maintaining crew in a state of deep hypothermia for weeks at a time. Their designs envision crew members cycling through periods of metabolic suppression lasting 14 days at a time, managed by automated medical systems, with periodic rewarming for medical assessment. The technology is not operational. It is a research and development program, but it represents genuine, funded, serious scientific work rather than speculation. Even if the SpaceWorks approach or something like it is developed to operational maturity, however, what it provides is not true suspended animation. It is metabolic reduction. The crew still ages, just more slowly. For a journey of 20 years, reducing metabolic rate by 70% extends the effective biological time of the journey, but does not eliminate it. The crew that arrives is still biologically older than they departed, and still subject to the cumulative radiation damage of 20 years in deep space, which the reduced metabolic rate does not protect against. The deeper biological escape, the one that would truly solve the lifespan problem, is not hibernation, but life extension. If human lifespan could be extended to hundreds or thousands of years by biological or technological means, then the journey times of interstellar travel become manageable in a very different way. You simply live long enough to complete the journey? This is not a purely fictional concept. The biology of aging has become one of the most active and well-funded areas of scientific research, driven partly by the aging demographics of wealthy societies and partly by genuine advances in our understanding of the molecular mechanisms of cellular aging. The hallmarks of aging, telomere shortening, mitochondrial dysfunction, cellular senescence, epigenetic drift, loss of proteostasis, are increasingly well understood as specific mechanistic processes rather than mysterious, inevitable deterioration. Companies and research programs studying the reversal of these processes are operating not at the fringe of science, but at major research universities and well-funded private laboratories. The results, so far, are encouraging in model organisms and cautious in human applications. In laboratory mice, interventions including senolytics, drugs that selectively eliminate senescent cells, telomerase activation, and partial epigenetic reprogramming have produced dramatic extensions of healthy lifespan and in some cases apparent reversal of specific aging markers. Dogs in clinical trials have shown early positive signals. Human trials of various anti-aging interventions are underway or planned. The honest scientific assessment is that meaningful life extension in humans, extending healthy lifespan by decades, perhaps eventually by centuries, is a realistic possibility within the next 50 to 100 years, if the current trajectory of the field continues. It is not a certainty. The biology of human aging is more complex than that of model organisms. The regulatory pathway for interventions aimed at the aging process itself is underdeveloped. The social and economic implications of dramatically extended human lifespan are so profound that they would reshape civilization in ways that are difficult to predict. It is worth pausing on what that reshaping would actually look like, because it is directly relevant to the interstellar question. A society in which people routinely live to 300 or 400 years is a society whose relationship to long-duration projects has been fundamentally transformed. The reason that institutions and civilizations struggle to maintain focus on projects that span more than a single human lifetime is, in large part, the reason that human lifetimes are short. Decision makers age out of their positions. Institutional memory fades. The people who understood the original motivation for a program die and are replaced by people who know the program only through documents and traditions. A civilization of people with centuries of individual experience. People who personally remember the first fusion experiment, the first interstellar probe launch, the first successful life extension trial, would have a relationship to continuity and long-range planning that is qualitatively different from ours. The psychological barriers to committing to a project whose payoff is 500 years away would look very different to someone who might personally live to see it. But if life extension becomes biologically real, if the generation born in the 22nd century routinely lives to 300 or 500 years, then the interstellar travel problem looks fundamentally different. The journey to Proxima Centauri, taking 40 to 80 years on a fusion drive, is not a civilization-ending commitment for a crew that has centuries ahead of them. It is an extended voyage, difficult, dangerous, isolating, but survivable in a way that it is not for beings with our current 90-year lifespan. Life extension is not a certainty. It is a research direction. An interstellar travel contingent on first solving the problem of biological aging is interstellar travel on a timeline of decades to centuries at minimum, and only if the science works out the way the optimists hope. But it is the most plausible biological escape from the lifespan constraint, and it is worth naming clearly. If we solve aging, the stars become at least conceptually reachable without the ethical nightmares of the generation ship. There is one more biological concept worth examining here, and it sits at the boundary between biology and philosophy in a way that makes it deeply uncomfortable to discuss, but important to take seriously. That concept is digital consciousness, the possibility of uploading the informational content of a human mind to a digital substrate that could survive the journey without biological degradation, and reconstituting a biological body at the destination from genetic information stored aboard. The traveler is not a biological person during the transit. The traveler is information running on radiation-hardened computing hardware, stored redundantly, immune to the biological consequences of the interstellar radiation environment and the passage of time. At arrival, the information is used to grow a new biological body, possibly from stored embryos, possibly from synthesized DNA, and the mind is transferred back into biology. The philosophical problems with this concept are not small. Is the entity that arrives at Proxima Centauri the same entity that departed? If the original biological person died on Earth, and only their information pattern was transmitted, what moral continuity exists between departure and arrival? Is the uploaded mind conscious in any meaningful sense during transit, or merely stored? Can consciousness even be meaningfully instantiated on a digital substrate? Or are there biological properties of neural function that cannot be computationally reproduced. These are not questions that current neuroscience or philosophy of mind can definitively answer. The relationship between neural information processing and conscious experience remains one of the deepest unsolved problems in science. We do not have a scientific theory of consciousness adequate to determine whether a digital simulation of a brain would be conscious or whether it would merely behave as if it were. What we do know is that this approach, if it ever becomes technically feasible, which requires solving both the mind uploading problem and the body reconstruction problem, neither of which is close, would represent a radical departure from biological interstellar travel. It would be interstellar travel without biology in the transit phase. And whether the entity that arrives is meaningfully the same as the entity that departed is a question that the traveler themselves would have a very strong interest in answering correctly before they boarded. Chapter 8: The von Neumann Alternative and What It Means for Us. There is a version of interstellar expansion that does not face any of the problems we have been discussing. It does not require solving radiation shielding. It does not require life extension or suspended animation. It does not require generation ships or the ethical nightmare of involuntary cosmic confinement. It does not require propulsion systems beyond anything in current engineering. It does not require a crew at all. It is the self-replicating probe, the concept first systematically described by mathematician John von Neumann in the 1940s and applied to the context of interstellar exploration by various researchers since. The idea is straightforward in principle. Build a probe capable of traveling to another star system, mining raw materials from that system, using those materials to construct copies of itself, and sending those copies to further star systems. Each generation of probes propagates to multiple new systems, each of which propagates to multiple further systems. The expansion is exponential. A single properly designed self-replicating probe launched from Earth could, in principle, explore the entire galaxy within a few million years. Not with human passengers, but with the instruments, the AI systems, and the fabrication capabilities required to characterize every star system and potentially build human habitable infrastructure awaiting the much slower arrival of biological beings. The physics of this is not problematic in the way that crude interstellar travel is problematic. Small probes, gram scale or kilogram scale, can be accelerated to significant fractions of the speed of light with far less energy than crude spacecraft. Light sails propelled by directed energy are genuinely tractable for small probes. The breakthrough starshot concept, which we discussed earlier, is essentially a first attempt at exactly this approach, and its designers explicitly envision it as the leading edge of a much longer-term program of increasingly capable probe technology. The von Neumann probe concept is interesting not just as a technology proposal, but as a window into a broader question that is worth asking directly. Is the goal of interstellar expansion the expansion of human biology, or the expansion of human civilization? Information and influence? Because these are not the same goal. And conflating them has led to a great deal of confused thinking about what interstellar travel is actually for. If the goal is to put biological human beings on planets orbiting other stars, to have living, breathing, eating, reproducing humans in another solar system, then all of the constraints we have discussed are real and severe. Biology is the constraint. The human body is the constraint. The lifespan, the radiation sensitivity, the psychological requirements, the gravitational needs, all of these become engineering requirements that the spacecraft must meet. And meeting all of them simultaneously at the scales and durations required for interstellar travel is extraordinarily difficult. But if the goal is the continuation of human civilization, the preservation and propagation of human knowledge, values, culture, and identity beyond the single solar system that currently contains all of it, then the biological requirement is not the only path. Information is lighter than bodies. Machines are more radiation tolerant than neurons. AI systems with human-level intelligence and human-derived values could, in principle, serve as the vanguard of human civilization's expansion, preparing the ground for eventual biological arrival on timescales that biology cannot achieve directly. This is not a popular framing in public discussions of space exploration, because it lacks the visceral appeal of the human explorer standing on alien soil. It lacks the narrative pull of a crew facing the void. It is harder to make a YouTube video about, or a movie, or a novel. The romance of space exploration has always been about human beings in space. Real people with real bodies experiencing real environments with real risk and real triumph. But the physics does not care about the romance. And the honestly unsentimental conclusion that the physics leads toward is this: if the goal is to survive as a civilization beyond the death of our sun, or to escape whatever catastrophe threatens Earth on a timescale of millions of years, the most efficient path is not to send biological humans to other stars. It is to send the information that constitutes human civilization, the knowledge, the culture, the accumulated learning, possibly the mind uploads or the embryos, or the genetic libraries, to other stars, aboard machines that can survive the journey and build the infrastructure for eventual biological habitation. The romantic vision and the practical solution are not the same thing. And part of being honest about the difficulty of interstellar travel is being honest about the possibility that the romantic vision, the human explorer, the generation ship, the colonists stepping onto alien soil under an alien sun, may not be the version of this that actually happens first, or perhaps ever, in the form we have imagined it. There is a second and sharper version of this discomfort, and it concerns not the probes themselves, but what they imply about the nature of human identity and the purpose of civilizational expansion. If human civilization can be meaningfully represented by information, by AI systems trained on human values, by genetic libraries, by cultural archives, and if that information can survive the interstellar journey aboard machines where biological humans cannot, then in what sense is it human expansion at all? The entity that arrives at Proxima Centauri aboard a von Neumann probe is not a human being. It is a machine carrying a representation of humanity. Whether that representation is sufficient, whether the descendants of those machines, if they eventually reconstruct biological humans at the destination, are meaningfully the descendants of the people who built the probes, is a question without an obvious answer. It touches on questions of identity and continuity that philosophy has wrestled with for millennia, and that the prospect of interstellar travel makes urgently practical. The von Neumann probe is an uncomfortable idea for another reason too, one that the physicist Enrico Fermi articulated in 1950 in a lunchtime conversation that has haunted the field of astrobiology ever since. If self-replicating probes are technically feasible for our civilization, if we can build them within the next few centuries, using plausible extrapolations of current technology, then any civilization sufficiently advanced to have developed space travel at all should have been able to build them millions of years ago. And a probe fleet launched millions of years ago, replicating and spreading at even a modest fraction of the speed of light, should have reached Earth long before humans existed. It should have reached every star in the galaxy many times over. So where is everybody? This is the Fermi paradox in its most sharp formulation. The galaxy is old, 13.6 billion years old. The formation of rocky planets around sun-like stars began billions of years before the formation of our solar system. There has been ample time, by any reasonable calculation, for a technological civilization to have arisen, developed self-replicating probe technology, and spread its influence across the entire galaxy many times over before our sun even formed. The universe is silent. We see no megastructures. We detect no Dyson spheres. We receive no signals. The galaxy, as far as our instruments can determine, is empty of any technological civilization except our own, or at least empty of any civilization that has made itself detectable. The Fermi paradox has many proposed resolutions, and it is not the primary focus of this video, but it is relevant here because it intersects with the question we are exploring. If interstellar travel is as difficult as the physics suggests, if the barriers to crude interstellar travel are as severe as we have been cataloging, then perhaps the silence of the galaxy is not so surprising. Perhaps the distance is the filter. Perhaps the combination of the energy requirements and the biological constraints and the engineering challenges and the social sustainability problems of generation ships represents a barrier so formidable that most civilizations, even those technologically advanced enough to understand the problem clearly, never overcome it. The physicist Geoffrey Landis proposed what he called the percolation theory of interstellar colonization. The idea that the spread of civilization through the galaxy is not a continuous wave front, but a percolating network, with gaps, with civilizations that choose not to colonize further, with physical and social barriers that interrupt the spread. In Landis's model, the galaxy might have many isolated civilizations that have not spread because the distance is genuinely too hard, and the silence we observe is exactly what the physics would predict. There is a variant of this hypothesis that is darker and worth stating plainly. Perhaps the silence of the galaxy is not the result of distance alone. Perhaps there is a filter, a step in the development of technological civilization so difficult, so rarely successfully navigated, that most civilizations that reach our level of technology do not survive long enough to develop interstellar capability. We reached nuclear weapons before we reached stable global governance. We are generating climate change faster than we are generating the political institutions capable of managing it. The same intelligence that produces the physics of spaceflight also produces the weapons and the environmental pressures that could end the civilization doing the physics. If the filter lies ahead of us rather than behind us, if it is the challenge of surviving long enough and developing stably enough to bridge the gap between current technology and interstellar capability. Then the Fermi paradox is not a puzzle about where everyone is. It is a warning about what happens to species like us. The Fermi paradox does not prove that interstellar travel is impossible, but the silence of the galaxy is at least consistent with the proposition that the barriers we have been cataloging are not merely engineering challenges that a sufficiently advanced civilization will eventually solve. They may be deep enough, fundamental enough, rooted enough in the laws of physics and the constraints of biology that they persist as barriers even for civilizations far more advanced than ours. That possibility, the possibility that the stars are simply too far away, that the universe has structured itself in a way that permanently isolates technological civilizations from one another, is one that we should take seriously. Not with despair, but with the intellectual honesty that science demands. Chapter 9: What the universe might actually allow. We have spent most of this video cataloging barriers, distance, propulsion, radiation, lifespan, psychology, social sustainability, the tyranny of the rocket equation, the silence of the galaxy. It would be easy at this point to read the cumulative weight of all of that as a verdict. Interstellar travel is impossible. End of conversation. That is not the right conclusion. The right conclusion is more precise and more interesting. It is this: interstellar travel as it is usually imagined in the popular conception, human beings in spacecraft, departing and arriving within human lifetimes, exploring alien worlds with their own biological eyes, returning to Earth with stories and samples and knowledge, is not possible with current technology, and faces barriers deep enough that it may not be possible within the next century or two, even with aggressive technological development. But human civilization reaching the stars, in some form, over very long timescales? That is a different question. And the physics says something different about that question. Let us separate the timescales. On a timescale of decades, the next 50 years, what is actually achievable in interstellar exploration? The most credible answer is robotic probes to Proxima Centauri, possibly using directed energy light sail technology along the lines of breakthrough starshot. Not crude missions. Not anything that carries a living human passenger. But instruments capable of imaging the Proxima system, characterizing its planets, measuring the radiation environment, detecting atmospheric chemistry. The scouting mission that would precede any eventual crewed mission by centuries. On a timescale of centuries, 100 to 500 years, what might become possible? If fusion energy is solved and the engineering of fusion propulsion is developed, crewed missions to nearby star systems become at least technically conceivable, though the biological and social challenges we have discussed remain. If life extension biology matures to the point where healthy human lifespans of several centuries are achievable, the crew of such a mission could survive the journey biologically. If closed-loop life support is developed to the reliability required for multi-decade isolated operation, the engineering of the spacecraft becomes tractable. None of these technologies is certain, but none of them violates any law of physics. They are, in the strict sense, possible. On a timescale of millennia, 1,000 to 10,000 years, if human civilization persists and continues to develop, the possibility space expands further. A Kardashev Type 2 civilization, harvesting the energy of its star, has energy resources sufficient to accelerate substantial masses to significant fractions of the speed of light. The timelines become shorter. The journeys become survivable within even current biological lifespans, if the crew is young enough at departure and the destination is within a few dozen light years. The galaxy, on this timescale, begins to open up, not quickly, not easily, not without cost, but open. The key variable in all of this is time, not the time of the journey, but the time of human civilization's development. We are, in the broadest possible perspective, a young species. Homo sapiens has existed for approximately 300,000 years. We have had writing for about 5,000 years. We have had physics as a mature science for about 400 years. We have had spaceflight for about 70 years. We are at the very, very beginning of our technological development, and extrapolating from where we are now to what will or will not be possible in 10,000 years is an exercise in humility as much as in projection. The stars are not going anywhere. Proxima Centauri will be approximately where it is now for billions of years. The galaxy is not on a deadline that human civilization needs to meet. The absence of a path to interstellar travel today does not mean the permanent absence of such a path. It means we are earlier in our development than such a path requires. But this framing, the long arc, the patient development, the eventual opening of the galaxy over thousands of years, also requires something that is uncomfortable to say in a culture that thinks in electoral cycles and quarterly earnings reports and 5-year plans. It requires civilizational continuity. The most fundamental prerequisite for interstellar travel is not a propulsion system. It is not a radiation shield. It is not a biological age reversal therapy. It is the continuation of human civilization in a form capable of accumulating knowledge and technology over very long timescales without catastrophic interruption. Every century of scientific and technological progress requires the survival of the civilization that produced it. Every breakthrough in fusion physics, every advance in life extension biology, every improvement in closed-loop life support, every development of AI systems capable of navigating interstellar space, all of it requires that human civilization persists long enough to develop it. A global catastrophe that sets back human technological development by 1,000 years does not merely delay interstellar travel by 1,000 years. It delays it by more, because the cumulative knowledge base that was building toward the required technologies must be rebuilt from scratch, and the rebuilding is never as fast as the original development. The existential risks to human civilization, the risks of the kind of catastrophic interruption that could derail this long development, are themselves a topic of growing serious scientific attention. The risk of asteroid or comet impact, while low in any given century, is not zero on timescales of thousands of years. The risk of pandemic disease, the risk of nuclear conflict, the risk of climate change reaching tipping points that undermine agricultural civilization, the risk of emerging technologies, artificial intelligence, synthetic biology, developing in ways that are catastrophic to human welfare. These are not science fiction scenarios. They are documented, studied, quantified risks that serious researchers at serious institutions spend their careers evaluating. The irony embedded in the interstellar travel problem. the deep structural irony is this. The primary argument for interstellar travel is that it provides insurance against exactly the kind of civilizational catastrophe that could prevent us from ever developing interstellar travel. We want to colonize other star systems to survive the death of our sun, or the impact of a large asteroid, or whatever catastrophe might otherwise end human civilization permanently. But we cannot reach other star systems until we have developed the technology to do so. And we cannot develop that technology if our civilization is destroyed by an asteroid or a pandemic or a nuclear war before we reach the required level. The bootstrap problem of civilizational survival is circular in a way that might seem paralyzing if you think about it too long. But it is not paralyzing because it has a practical implication that is clear and actionable. The most important thing a civilization can do to increase its probability of eventually reaching the stars is to ensure its own continuation on the timescale required to develop the technology to do so, which means that the mitigation of existential risks, the serious, funded, scientifically grounded work of protecting civilization from the threats that could end it, is not separate from the project of interstellar exploration. It is the precondition of it. You cannot explore the galaxy if you do not survive the next 1,000 years. Conclusion. Let us come back to the beginning, to the clear night, to the vertigo of looking up. The stars are there. They are real. They have planets, many of them. Those planets, some of them, have the chemical and physical conditions that could sustain life. Proxima Centauri b, the rocky, roughly Earth-mass planet orbiting in the habitable zone of our nearest stellar neighbor, is one of the most scientifically compelling objects ever detected, not because we know it is habitable, but because we know it is there, and it is close, and it is the kind of world that, in the right conditions, could be like ours, and we cannot reach it. Not now. Not with anything we have or are likely to have within the lifetime of anyone reading this. The distance is too great, the physics too constraining, the biology too fragile, the engineering too far beyond current capability. The honest answer to the question posed by this video's title, whether even the nearest star might be too distant for humans, is for human beings as we currently are, with current technology, on any planning horizon shorter than several centuries, yes, it probably is. That is a hard thing to sit with. It runs against the grain of a civilization that has spent the past century training itself through the Apollo program and the science fiction genre and the entire cultural apparatus of space exploration to believe that the universe is accessible, that if we try hard enough, invest enough, imagine boldly enough, we can go wherever we point ourselves. The universe is not obligated to conform to that belief. But here is what the universe does offer, and it is not nothing. It is, in fact, extraordinary. It offers the proof that it can be done. Not by us, not yet, not in any form we currently have access to. But the laws of physics, properly read, do not forbid human civilization from eventually reaching the stars. They impose constraints, severe constraints, that will require centuries of development and technologies that do not yet exist. But constraints are not prohibitions. The laws of physics permitted flight for billions of years before anything alive was capable of it. They permitted nuclear energy for the entire history of the universe before any species learned to extract it. They will continue to permit interstellar travel whether or not any civilization ever achieves it. What we know, sitting here at the beginning of the space age, the very, very beginning of it, a few decades into a project that may take millennia, is this: the universe is coherent. The same laws that govern the acceleration of the Parker Solar Probe govern the dynamics of distant stars. The same chemistry that built life on Earth operates in the interstellar medium. The same physics that describes our Sun describes Proxima Centauri. The universe does not contain separate physics for here and there. It is one system operating by one set of rules, and those rules are discoverable and applicable by beings intelligent enough to read them. That coherence, the fact that the universe operates by consistent, discoverable laws rather than arbitrary divine caprice, is the most important thing physics has ever told us about the stars. It tells us that they are reachable, not in the sense of being easy or near, but in the sense of being, in principle, accessible to beings who understand the rules well enough. And we have been learning the rules faster in the past 400 years than in the entire previous history of our species. The nearest star is probably too distant for humans as we are now. But the key word is now. We are early. We are at the beginning of a species that, if it survives, will have tens of thousands of years of development ahead of it. Development that will change what we know, what we can do, what we are biologically, what we are technologically. Whether interstellar travel is in that future depends less on the physics than it does on choices, on whether we invest in the science seriously and honestly, rather than through the lens of short-term political cycles, on whether we protect the civilization that is developing the science from the catastrophic risks that could interrupt it, on whether we are honest about the magnitude of the challenge rather than pretending it is simply an engineering problem awaiting a clever solution, and on whether we accept, with the intellectual maturity that the actual scale of the universe demands, that some of the most important things we will ever do may be done by our descendants, across timescales that extend far beyond any individual life, that the contribution of our generation may not be to go to the stars, but to ensure that the civilization that eventually does still exists, that the work of laying foundations, of developing the physics, the biology, the propulsion technology, the ethical frameworks for what interstellar colonization means, is itself the great work, even when we cannot see the building it will support. The stars have been burning for billions of years. They will burn for billions more. They are patient in ways that we are not. The question is not whether the nearest star is reachable. Physics says it is, in principle. The question is who reaches it, and when, and in what form, and carrying what of what we are. And the answer to that question depends on what we do with the time we have. Which is, when you hold it plainly in the dark under those stars, a deeply human kind of answer. Not the one we wanted, but the one that is true.